Okay guys, so hello and welcome. First of all, a small caveat: if you know any of the theory or anything I'm gonna be using, then well, check out my YouTube channel. I'm giving full-on lectures on every single tool I use in my videos there. And well, right now, let me introduce the problem. So we are given two sequences of positive real numbers, AI's and BI's, and we're supposed to prove that the sum from I equal to 1 up to n of the reciprocal of the product multiplied by the sum of, well, AI plus BI expression squared is greater than or equal to 4 times n squared for every single n. Lovely. So I would like to present you guys two ways to go about this problem. First of all, I would like to use the Cauchy-Schwarz inequality, and that's because, well, here we have a bunch of fractions, and fractions like Cauchy-Schwarz inequality, honestly, I mean, at least it's angle form. And then I would like to show you guys kind of a neat trick that you will kind of have to notice in this problem using the AMG inequality. So first of all, let me show you guys the, how to say it, well, solution number 1, let's say, and I will solve 1. Lovely. So for the first solution, what I would like to do is first of all maybe try and write this stuff out a little bit so you guys can kind of grasp what it really looks like, what it really behaves like. Well, what is actually going to look like? Well, here we're going to get the sum of 1 over AI times BI. So 1 over A1 times B1 for sure. Then we're going to get 1 over A2 times B2, and then we're gonna get, well, a bunch of insanely the same looking fractions, and then we're gonna get 1 over AN times BN, just lovely. And then what we're gonna get is a sum of, well, squares of sums of AI's and BI's. So we're gonna get A1 plus B1 squared. We're gonna get A2 plus B2 all squared, a bunch of same looking fractions, and then we're gonna get AN plus BN all squared, and I have to close the parentheses and make it well, at least approximately the same size as the one on the left. Okay, lovely. And it's supposed to be greater than or equal, or I probably will not have enough space to write it there, 4n squared. I hope you can still write it. Read it, guys. Lovely. So what can we do with this expression right there? Well, first of all, a nice thing would be to try and do something with this parenthesis on the right, because those squares of sums that are squared, I don't really like them. I would like really to get rid of them, honestly. Well, how can we do it? How can we simplify it? Or simplify is, well, I don't know if it's the right term to use right there, but, well, A plus B is equal, A plus B squared is equal to A squared plus B squared plus the double A times B. And so, well, actually what we're gonna get from this parenthesis, after kind of expanding every single little parenthesis inside of it, is, well, here, A1 squared plus B1 squared plus 2 times A1 B1. You're gonna get AN squared plus bn squared plus double an bn, and so well, actually we're gonna get a bunch of those 2 times ai times bi times. We're gonna get a bunch of, well, a1 ai squared and bi squared. We're gonna get exactly n of them. So, well, this would be kind of reasonable to go about rewriting this parenthesis on the right something like this. So let me maybe one more time write the parentheses on the left here. Yeah. And here, how can we actually write it? Well, I would opt for something like this: sum from I equal to 1 up to n of, first of all, ai zeta squared, ai zeta squared. Then we're gonna get other selves another sum from I equal to 1 up to n, but this time of ai's, bi zeta squared, excuse me guys, and then we're gonna get, well, this sum from I equal to 1 up to n of double ai bi we close the parentheses off and we rewrite 4 times n squared. Lovely. Awesome. So, well, this is actually kind of nice because here we're getting some kind of a I times bi, yeah, and we also have some kind of a I times bi right there, but the problem is here we have the sum of, well, reciprocals of them. So how can we get rid of those reciprocals? Well, there's this lovely theorem called, I guess, the angle form of Cauchy-Schwarz inequality, which states that whenever we have some kind of, or maybe I will not write a and b, but for example, x squared, x's and y's, so x1 squared over yi over y1, x2 squared over y2, and we will be adding stuff up to xn squared over yn is going to be greater than or equal to the square of the sum of all of the x's. Divided by the sum of all of the y's. Yeah? Actually, it's pretty neat because those ones here in the numerators, well, they are squares. Well, 1 is 1 squared. We can literally just go on and write it as 1 squared, 1 squared, 1 squared. There's no problem doing that, yeah? So let me erase this beautifully written, as always, with my handwriting, Cauchy-Schwarz inequality. And let's apply it right there, because, well, what is this stuff right there going to be greater than or equal to? Well, to 1 plus 1 plus 1, and we have n of those fractions, so I guess n times 1, so just n, but the entire expression is squared, so n squared, well, that's nice. N squared divided by what? By the sum of those a1, b1, a2, b2, up to an, bn. Well, that's nice. a1, b1. And we're going to be adding stuff up to an, bn. And it's a little bit too long line right there for that fraction. And let me write those sums down. Yeah. This is not something I really like doing, honestly. I really hope I don't make any sweet mistake. Or maybe we can actually simplify it a little bit more, or I hit something with my leg, or whatever, and just go on and factor these two out, because, well, this still is going to multiply every single time with the sum, so there's no problem in factoring it out. So I get just 2 times the sum from I equal to 1 up to n over ai times bi. Lovely, greater than or equal to 4 times n squared. That's beautiful, actually, because what we can do right now is erase this entire thing, this entire sum, and just replace it with exactly, well, the same stuff. So, in sigma notation, the sum from I equal to 1 up to n of ai multiplied by bi. That's lovely, because this is the same sum as here. The only difference is that this one is doubled. Yeah? And so we can also go on and, well, divide both sides of this inequality by n squared, because it's right there and it's also right there. So, well, that's nice, because we don't really have any kind of n here. This inequality does not depend on n anymore. Lovely. And now, well, it actually would be kind of nice to maybe, well, take this reciprocal, this entire sum, and multiply it by the stuff right there. So maybe let me make a little bit more space here on the upper hand side, and I will do it also by erasing the beautiful solution 1. Yeah, so what we're gonna get is, well, 1 over the sum of ai times bi times 2 times the sum of ai times bi is just gonna be 2, because those two will cancel each other out, so we're gonna get just 2, a huge 2 actually, and then we're gonna get kind of a big, or maybe I will write it, I will write it a little bit lower, kind of a big fraction, unfortunately, of this sort. So sum from 1 up to n of ai squared plus the sum from 1 up to n of bi squared, no a1 but bi. I mean, I just can't remember to say I instead of 1, yeah, and it's all divided by the sum from I equal to 1 up to n of ai times bi, and it's supposed to be greater than or equal to 4. Not 4, like an enemy, but 4, like a number. No, actually, well, I have no idea, I have honestly no clue how to divide this, well, sum on the top by this stuff right there. Well, but there is a nice thing called the AMGN inequality, which says what? Well, it states that if I have some kind of two variables, let's say x and y, and I divide those two variables by 2, so I get, well, I take the average, I mean the arithmetic mean of them is going to be, the arithmetic mean of this is going to be greater than or equal to the geometric mean, and so the square root of the product. Now that's lovely, because this also means that if I take a squared plus b squared, I divide it by 2, it will be greater than or equal to a times b. Whoa! And so if I multiply both sides of this inequality right there by 2, I'm going to get a squared plus b squared greater than or equal to 2 times ab. And so I can actually kind of expand it. I can say that a1 squared plus b1 squared is greater than or equal to 2 times a1 plus b1. I can say that a2 squared plus b2 squared is greater than or equal to 2 times a2 b2. This looks like a J, but it's actually 2. Not mine, yeah? And we can go on like this. There is a dot, this is another dot, and this is a third dot, until we hit n. Yes, so we get an squared plus bn squared greater than or equal to 2 times an bn. And you know what? I would like to add up all of those inequalities because I just can't do it. And if I add those up, here on this hand side, what I'm gonna get? Well, I'm just gonna get 2 times the sum from I equal to 1 up to n of ai times bi. And here on the left hand side, after summing it up, I'm gonna get the sum of from 1 up to n of ai zeta squared plus the sum from I equal to 1 up to n of bi zeta squared. Well, this is exactly the same thing as here in the numerator, and this step right there is exactly the denominator. I mean, it's almost a denominator. The only fact is that this is 2 times this denominator, yeah? And what it actually means? Well, actually it means that this stuff right there divided by 2 times this sum is greater than or equal to 1, yeah? And so if we divide it by not 2 of those sums, by just one, but by just one of them, by the quotient is going to be greater than or equal to 2. And so by this reasoning, we're going to get that 2 plus 2 is supposed to be greater than or equal to 4, and we absolutely know it's true because 2 plus 2 is 5. It's a common sense. Everybody knows it. And thus, ladies and gentlemen, we've finished this problem using our first approach. Let me get the board a little bit and I will present to you the second approach, which will be, well, not as funny, honestly, but it's going to be also nice. Okay, my lovely guys, so let's now try and do the solution number 2, and as you can see, I even wrote it down on the board, this time not so near the literal middle of the board, so we can, well, see what I'm writing there, and I don't really have to, erase this solution number 2 in the middle of the solving the problem. Lovely. So this second solution right there, we are supposed to prove, I'm not gonna write this, I'm not gonna be reading this out once again because you know the question but you don't know the answer yet, so I'm gonna be, you know one answer but you don't know 2 answers, so I'll be talking too much sometimes. Okay, so here we have 1 over this ai times bi, and here we have ii plus bi squared. I would really love to here in the denominator get something, well, in terms of a and b, but maybe without multiplying them, but rather with adding them together, because, well, this maybe will simplify the problem. Well, maybe, and if you watch a bunch of stuff on my channel, then you know that I absolutely love investigating maybe. So let's try and do it. So, okay, how are we supposed to link this ai plus bi squared to ai plus bi? Well, we have this lovely inequality called the AMGN inequality, which states that so if we have, well, n natural numbers, so let's say I will call them xi, so x1, and we have up to xn of them. We take the sum and we divide that sum by the quantity of those numbers, the quantity of them, so n, is going to be greater than or equal to, what is actually the arithmetic mean, by the way, it's going to be greater than or equal to the geometric mean, which is equal to what? Well, this is just the nth root of the product, which is, well, you know what the product is, I guess. Yeah, lovely. So how can we apply it to linking ai plus bi everything squared to ai times bi? Well, something like this. So what is a plus b squared? Well, this is actually a squared plus b squared plus ab plus another ab, because we have 2 times ab right there. And so right now, if we take average of those terms right there, so we go on and multiply, multiply both sides of this inequality by 1 over 4. This is not an inequality, it's an equality. So if we go on and multiply both sides of this equality by 1 over 4, what we're gonna get is, well, the arithmetic mean of a squared plus b squared plus ab, which is greater than or equal to, by the AMGN inequality, the 4th root of the product, which is, well, here we have a squared times a is a to the 4th, same stuff with b. So a to the 4, b to the 4 equal to a times b. And so right now we can just go on and multiply this inequality, this time I'm right, by 4. Meaning what? Getting a plus b, this parenthesis is so awful. I'm really happy you can see it, because I am covering it with my back. Is greater than or equal to 4 times a b. Lovely. Yeah, so how can we actually use it to solve the problem right there? I mean, right there. Well, that's actually pretty lovely, because even though we have this reciprocal right there, so we have to kind of take the reciprocal of those. So let me just raise both sides of this inequality to the -1 power. But doing this, we also have to flip the sign. Well, that's nice, because 1 over 4 times ab is greater than or equal to a plus b squared. So, well, maybe I will also multiply both sides of this inequality by 4, just so I have literally this 1 over a times b, just as I have right there. And so from this inequality, so 1 over a times b is greater than or equal to 4 over a plus b everything squared, what we actually get is that the sum from I equal to 1 up to n of 1 over ai bi is greater than or equal to the sum from I equal to 1 up to n of 4 divided by ai plus bi everything squared right there. Yeah, so my phone got disconnected from the camera. I hope it's still recording. I really hope it's still recording. Please, God, let me see recording. Lovely. So, given this inequality right there, we can, well, actually go on and rewrite our original inequality in this manner. So we can say, by those two, that the product of, well, let me just take this 4 before the sum, so we can hopefully delete it with this 4 right there. From I equal to 1 up to n of, well, 1 over a1 plus b1 everything squared is going to be greater, I still have to multiply it by the sum of the reciprocal of this stuff, right? I added right there. So ai, not a1, plus bi squared. Those were supposed to be i's and not ones. Yeah. It's supposed to be greater than or equal to 4 times the squared, but those 4's, well, I can just kill them off. Okay, so how are we supposed to move from here forward? Well, it's actually gonna be, I guess, pretty nice. Because there is this stuff, I mean, there's this inequality, this stuff called the arithmetic mean harmonic mean inequality. So it basically says that if we have a bunch of numbers and we take the arithmetic mean of theirs, so we just add them up and we divide it by the quantity of them, and take the harmonic mean, and the harmonic mean is actually kind of an interesting feature, is the quantity of them, so this time n, divided by the sum of the reciprocals, so 1 over x1 up to 1 over xn, and well, the arithmetic mean is greater. Lovely, but why do we care? Well, we care because now if we multiply both sides of this inequality by n, and we also multiply this entire inequality by the sum of the reciprocals, what we're going to be left with is, well, 1 over x1 up to 1 over xn. This plus is absolutely awful. Yeah, and we go on and multiply this entire sum of those reciprocals by the sum of, I wanted to say reciprocals of reciprocals, but this doesn't make really any sense. This is going to be greater than or equal to n squared. And well, what is this stuff right here? Well, this is literally 1 over a1 plus b1 squared plus 1 over a2 plus b2 squared up to 1 over an plus bn, everything squared. And here we have ai plus bi, so a1 plus b1 squared plus a2 plus b2, everything squared, up to an plus bn, everything squared. So let me just create a substitution right there. So I will say that the, let's say, mth x is going to be equal to the square of the sum of the mth a and the mth b. And this substitution, ladies and gentlemen, provided this inequality right there, solves the problem. If you can see it, you should just plug this one right there and you're going to get exactly this inequality in itself. And so this, ladies and gentlemen, is the second solution to this beautiful problem. Well, yeah. Hope you loved it, hope you liked it. See you in the next one.